Wait for 1 more minute. Okay, maybe we should start.
Yes,
Yeah.
sure.
Yeah. So welcome everyone to session A3. So we'll have 4 speakers today. And like I just said a minute back, so if you have any questions, let's all be on mute except for the speaker. And if you have any questions, maybe we'll raise our hand, and then in the Q&A time we can go through, all the hands raised. And let's get started. So the first talk is going to be on string indexing for top K close consecutive occurrences by Philip Beer, Inge Ligots, Eva Rotenberg, Teresa Anna Steiner, and Max Rishoy Pedersen. And Max will be giving the talk. Over to you, Max.
Thank you. Yes, so I'm Max, and I'll be presenting this work. In this paper, we look at a variant of the string indexing problem. So the classic string indexing problem is that we have a string S, and we want to pre-process it into a data structure such that at query time, when I come with a pattern P, I can quickly find all the occurrences of P in S. So an example here with a large S and a smaller P, we want to find all the positions in S where P occurs. And as I've said, we solve a variant of this problem called the top K close consecutive occurrences problem. So instead of just a query pattern P, we're also given an integer K, and we now want to find the K closest consecutive occurrences of P. So these are the K consecutive pairs of occurrences of P of smallest distance. So for our example here, say our query pattern P is AN and our K is 2. We want to find the 2 closest consecutive pairs. And in this case, it would be 11 and 13 and 6 and 11. Yes, we provide 2 trade-offs for this problem. Firstly, we provide an O of n log n space solution, and then we provide, and this has an optimal query time of O of m plus k, and here m is the length of the pattern P. And we also provide a linear space solution that has a query time of O of m plus k to the 1 plus epsilon. And here epsilon is any constant between 0 and 1. And I'll explain both trade-offs, and we'll start with the O of n log n space solution one. So the foundation of this trade-off is the heavy path decomposition of the suffix tree. And this is a suffix tree from the example string you saw before. And the bold edges are the heavy paths, and off the heavy paths hang the light edges in dotted lines. And then for essentially what we do is for every heavy path, we take the set of consecutive occurrences at all the nodes, and then we encode them as line segments, as vertical line segments. The interesting thing is here, for any consecutive occurrence that appears in this path, there is an interval in which it exists, and outside that interval, it doesn't exist. So we can encode every such consecutive occurrence as a line segment where the x coordinate is the distance of the pair, and the 2 y coordinates is the interval in depth on the heavy path where that consecutive occurrence exists. And this allows us to query, because when I come with my query pattern P and I land on such a heavy path, the problem is now reduced to simply finding the k leftmost line segments that intersect this horizontal line traced by the depth of the pattern P on the heavy path. So that's the first trade-off. The data structure is the heavy path decomposition of the suffix tree, and then we build such a line segment data structure for every heavy path, and this ends up taking O of n log n space. And the query time is optimal. We spend m time to find the locus of the pattern in the suffix tree, and then we query the line segment data structure for the given heavy path in O of k time, ending up at O of m plus k query time. That was the first trade-off. Now we go to the second and more involved trade-off, where we reduce the space to linear, and we pay for it in increased query time. the basis of this solution is a cluster decomposition of the suffix tree. So assume we knew k at indexing time when we build our data structure. Then what we do is we take the suffix tree and then we cluster it into clusters of nodes that have at most k nodes in such a way that there are two types of clusters. Firstly, we have the leaf clusters, which are the ones you see in the bottom here, which have only a single boundary node that is a node where they intersect another cluster. And then there are the path clusters, which have two boundary nodes. And we call then the path that run between the two boundary nodes for the spine. And this is the decomposition, and our data structure is then performing this decomposition. And then for every spine, we build the line segment data structure that we showed before, with the caveat that we only store the k leftmost or k closest consecutive occurrence at any depth in this line segment data structure. And because there are, due to the decomposition, O of n over k clusters, and each of them have O of k size, this ends up taking linear space. And now to query, we find a locus in the suffix tree as before. And if we end up on a spine, then it's simply a matter of querying the line segment data structure just as before, with the same query time as before. The other case is that we don't land on a spine. So we could land up in a small subtree that hangs off a spine. But because we're now in such a cluster, we are in a very small subtree. So even if we find all the occurrences of P and then construct all the consecutive occurrences and then select the k smallest ones, it doesn't end up taking more than O of m plus k time, because there can't be more than k occurrences of P and thus no more than k pairs. And the same thing is true if we land up in a leaf cluster. The problem is, of course, that in the real problem, we're not giving k at the construction time. It arrives in the query. So to solve this, we apply this fixed k solution recursively. So this is again the suffix tree, and initially we then cluster the suffix tree with cluster size square root n, and build the line segment data structure for every spine, storing up to square root n line segments at any depth. And then all the small subtrees that hang off the spines, we recursively cluster again building a line segment data structure for every spine. Of course, now the cluster size is smaller. Now it's the fourth root of n. And we keep doing this recursively until we reach a constant cluster size. And that's the data structure. This allows us to perform queries. Oh, sorry. Yes, of course, we can recursively cluster, keep doing this log n times, over log n times until we reach a constant cluster size. So it ends up taking O of n log n space. And this allows us now to query. When I come with my pattern P, I find the locus. And the interesting thing here is that I'm always going to land on the spine of some cluster, because we fully decompose the suffix tree. We keep doing it, or we end up in a constant size cluster. So we land up in some spine, and then there are exactly two cases. If k is smaller than the current cluster size, then we have enough pairs stored for the line segment data structure for this spine. So we can simply query the line segment data structure for the spine, and that's going to give us our correct result in O of m plus k time. However, k could also be larger, in which case we don't have enough line segments stored for the spine. But now we're in the case where we're actually hanging off a subtree of the cluster on the recursion level right above us. So there can't be that many occurrences of P in total. Specifically, there's going to be less than k squared. So even if we find, as before, all the occurrences of P and construct all the consecutive occurrences and select the k smallest one, this doesn't end up taking any more than O of m plus k time. And that's the gist of our solution. There's much more detail in the paper, of course, and also in the longer talk where I explained this more in depth. The two steps more before we reach our primary result here is that, firstly, we can reduce this O of n log n space to linear by some clever encoding. And then instead of simply clustering with square root n every time at every recursion level, we introduce a tunable parameter epsilon. So for a constant epsilon, we end up with this O of m plus k to the 1 plus epsilon query time. and still a linear space for constant epsilon. Yes, and this of course was very brief, and as I said, that more details in the paper, obviously. Yes, thank you.
Thank you. So if there are any questions, maybe you guys could raise your hand. Just unmute and speak up, please. So I have one. I mean, this is even not relevant for a theory talk, but so what is there? I mean, could you give us some motivation for why you want the closest pairs of occurrences?
Well, yes. So there's finding pairs of specific distances is a problem studied in our other context where we've seen before, and this was just a very natural extension of the classic string indexing problem that hadn't been studied before.
Okay.
So there are a lot of top queries in the document setting also, and we've also looked into, as has other authors looked into, finding pairs where the distance is some interval, and this was just an unstudied problem, though it's a very natural variant of string indexing.
And do people also look at the version where the longer string can change? Maybe you make some modifications to the string and so on, and you look at the update complexity of the data structure.
So the dynamic version of the problem, you mean?
Right.
Yes, I haven't thought a lot about that. That's actually very interesting. It seems to me to be much harder, but I'm actually not sure. I haven't thought too deeply about it, and I don't think I've read the dynamic versions of the other closed occurrences.
Okay.
Yeah.
Thank you.
Thank you.
So, yeah. So, any other questions? If not, maybe we could ask Nicholas to share screen, and then we can wait for a couple of minutes to start the next talk.
I'll stop sharing then.
Sure. Thank you. Thanks again.
Thank you.
Okay. Can you hear me? Can you see my screen?
Yes, we can hear you and see your screen. Maybe we'll wait for like a minute or two and then start.
So sorry, should I start? Or
maybe we'll wait for 1 minute in case somebody wants to join or something between. Yeah. Okay, so maybe we'll start the second talk. So this talk is, the title of the talk is Maximum Clique in Disk-like Intersection Graphs. It's by Edward Bonnet, Nicholas Greyer, and Till Milso. And Nicholas will be giving the talk. So maybe I'll mute myself and hand it over to Nicholas.
Okay, thank you. So yes, this talk will be about computational geometry. And so I'm going to try to give you some ideas and like another side of what we do, because I don't assume that everyone is familiar with computational geometry. So first here, you have already a picture of what is called a disk graph, but let me start by giving you a more precise definition. So we consider a graph G, and we say that G is a disk graph if it is possible to map the vertices of G into a set of closed disks into the plane, and such that two vertices in your graph are adjacent if and only if the corresponding disks intersect. So here, for example, we have a graph G, and we can wonder whether G is a disk graph. And it is indeed, because it has what is called a disk representation. So here, each vertex is mapped to a disk. So for example, this blue vertex here is mapped to this blue disk. And then, whenever you have two adjacent vertices in your graph, I don't know, for example, the blue and red vertices here, then you can see that the corresponding disks intersect, blue and red disks. On the contrary, for any pair of vertices that are not adjacent in the graph, say the red and green vertices, for example, then the red and green disk do not intersect. So this is the definition, and we can see that G is a disk graph because it has a disk representation. Then we can change the definition slightly just by making a new constraint, that is our set of closed disks in the plane must have unit radius. And then we speak of unit disk graph. Otherwise, you can see the definition is the same, this intersection property. And you can see that G, which was a disk graph, is also a unit disk graph because it has a unit disk representation here. So you can see it's exactly the same. I've just added this constraint that each disk has unit radius. Okay, so now let's go to maximum click. And so the story started when Clark, Colborn, and Johnson wrote this seminal paper where they showed how to compute a maximum click in unit disk graph. And then the algorithm requires a representation, meaning that the input should be, for example, the position of the centers of the unit disks. And then they show how to compute maximum click. And their proof was very elegant, and so we started a lot of further studies. In particular, this was extended 10 years later by Raghavan and Srinrad, who found a polynomial time algorithm again, this time that works even without a representation. So now the input is only an abstract graph, and the output is either a maximum click or a certificate that your graph is not a unit disk graph. So what we did is to generalize this result to something that I think is quite natural. So we have the same polytime algorithm, but now it's in intersection graphs of translates of C, where C is any fixed bounded convex set. So before it was unit disk, and now it's translates of a fixed bounded convex set. And this works also even without a representation. Okay, so now let's go from unit disk to disk of general radius. And there was a very recent result by Bonami et al., where they showed how you can compute, how you can solve maximum click with an efficient p-task. And this works even without a representation. And what we could do here again is to generalize this result. Before it was with translates, and now it's with homoflets. When you have unit disk, it was translate. When you have disk of any radius, it's homoflet. So again, it's kind of a natural generalization. However, for this theorem, we have a C that is bounded, convex, but also centrally symmetric, meaning that there is a point in C such that C is like you have a central symmetry around this point. And if you don't have this condition, we actually don't know what you can do. And just to give you some kind of idea of how we do that, is just like if you take such a set C, if you think about it, you can see that you can derive a norm from it. Like each such set C has a corresponding norm, which has a corresponding distance. And with unit disk, it's kind of working with the Euclidean distance. And when you are working with any set C, which is centrally symmetric, bounded, and convex, you have to work with any norm. So our proof for both actual results is to try to mimic the proofs that were written before, but now working with any norm instead of the Euclidean norm. So okay, this was for the positive result. We had this, for example, result by Bonami et al. But of course, there is the natural question: what is the complexity of maximum click in disk graphs? So this time with any radius. And this is actually considered as a very important problem in the field. It has been open since the 90s, and a lot of people have tried it, and we don't know anything yet. But it's mostly believed to be NP-hard. However, there are some reasons to think that the non-reduction techniques that you can find in the literature, we have some reasons to believe that this will not be enough to show NP-hardness. So what you can do then is just try to imagine some new reduction techniques. And how you can think of these techniques, it's, well, one thing you could do is just look at similar problems and try to show NP-hardness of similar problems. And what we could do is to show that maximum clique is NP-hard and even APX-hard in intersection graphs of unit disks and axis parallel rectangles. So such graphs are graphs like this, where you can find a representation where each vertex is mapped either to a unit disk or to an axis parallel rectangle in the plane. And then you have this same definition with intersection. And this is maybe even a surprising result, because we have seen that you can compute maximum clique in polytime for unit disk. We have seen that you can do, and here you can see that this is also possible in intersection graphs of axis parallel rectangles. But then somehow, if you allow your set to be represented by either unit disk or axis parallel rectangles, then the problem becomes really hard very fast. So, okay, so I'm not going to go into much more details. We do a reduction from max 3 sets. Yes, okay, just as a conclusion, this is like the theorem I've listed. And then let me make this final observation, that is that actually our reduction technique, if you look at the paper or if you listen to the longer talk, you will understand why it's more general than the techniques that were previously known, but it's still not enough to show NP-hardness for this graphs. So there are still some things to improve. So that's it. Thank you.
Thank you very much. Any questions? So if you have any questions, you can speak up, raise your hand in your talks. So one question again I had is this third theorem, maybe I missed it, but so the representation there is what it's given, the hardness.
Sorry for the hardness.
Yeah. The NP hardness or APX hardness. What's known? I mean, do you assume anything about the representation, or it's?
So it's given a representation.
Sorry.
It's given the representation. It's still NP.
Oh, it's given. Okay. I see. Okay.
Like yes, you are already given a set. Even if you are given a set of unit disks and rectangles,
that's what I was doing. Okay.
So yeah.
I see. So we have quite a bit of time before the next talk. So I guess, maybe we can. So should we go ahead, or should we like try to stick to the time?
If there is no further question, then I can stop sharing.
Yes, thanks again to Nicholas. And I guess the next talk is on the densest case of the planted models for the densest k-Subgraph problem by Yash. So maybe Yash, you could try sharing your screen. Yeah, we'll wait for a couple of minutes, I guess. So maybe we can get started with the next talk. So the next talk is on planted models for the densest k-subgraph problem by Yash Khanna and Anand Lewis. And Yash will be giving the talk. So over to you, Yash.
So hi all, I'll be talking about the densest k-subgraph problem. So let me just jump right in. So the problem is as follows. You are given an undirected and a possibly a weighted graph and a parameter k, and the goal is to output a subgraph on k vertices with the maximum average degree. So you are supposed to output a subgraph on k vertices with the maximum average degree. So just to get some notation right, um, the average degree of a subgraph tree, which I'll denote as delta t, is nothing but the summation of degree of all vertices u in t divided by 2 times t. The standard definition of average degree, and this I'll denote by delta t. So what is known about this problem? So firstly, it is known that this problem is NP hard because it is clearly a generalization of the k-clique problem. Also, on the algorithmic front, it is the best known approximation algorithm for this particular problem is a n raised to power 1 by 4 approximation algorithm. So this is by Bhaskar et al. Um, on the hardness side, it is known that this particular problem does not have a p-task unless NPS sub-exponential algorithms. And a recent result by Manu Rangsi shows that you can rule out n raised to power 1 upon log n to power c. So if you look at the second and the fourth result, the best we can do from the algorithmic side is n raised to power 1 by 4. But sort of the best we can the on the hardness side, the best we can rule out is only n raised to power 1 upon log n to power c. So this is not like really convincing. So it is natural to look into this problem into some special cases. So into some special families of graphs and so on. So we study this problem in semi-random models. So our model, the first semi-random model which we study is as follows. So we plant a dense subgraph of size k and average degree d in a random graph. So what I mean by that is x cross v minus s is a random graph with some parameter p, and v minus s is also a adversarial random graph. So you plant this subgraph S, and now what do you want to do with it? So a monotone adversary is allowed to modify anything but S. So you cannot remove the edges inside S, but any edges on the boundary of S or outside or within V minus S, a monotone adversary is allowed to remove. And the goal is to ideally recover S from this. So uh, and you can think of k comma d as some polynomials of n and p as some 1 upon poly of n. So we have set ourselves for a higher goal that instead of having an approximation algorithm, can we possibly recover the planted dense subgraph S? So this is a sort of generalization of the popular planted clique problem. So um, you can think of the restatement of the problem is as follows. What is the smallest value of d in terms of k, p, and n for which S can be recovered? So this is because the smaller the value of d, the harder it should be intuitively, right? The more the value of d, the more it will stand out. So in any algorithm, at least we intuitively feel that the higher values of d should be easy. So smallest value of d for which this can be recovered, and as I said, is a generalization of the planted clique problem. So this problem has been studied in the literature, and the work which gave a n raised to power 1 by 4 approximation in the worst case also studied this problem, and there d is some threshold like d is omega of np to the power log k base n, and our threshold is max of pk comma square root np. So let's try to compare them in different ranges of k. So we see that so the smaller the value, the better it is, right? So you see that in certain ranges our algorithm is better, or our threshold is better, and in some cases it is equal, and in some cases it is smaller. So, but let me also point out that in case there is also a spectral algorithm known when k is greater, much larger than root n by the same paper. So, in terms of the threshold, we are not doing anything new till now, but we also study our problem in more semi-random models. So, the second semi-random model is where v minus s is an expander graph. So the first one was where this is a this is a n minus k g n minus k comma p random graph, and this is a n minus k g prime comma lambda expander graph. So what do I mean by this n minus k d prime lambda expander? So it means that it is supported on n minus k vertices. It is a d prime regular graph, and lambda is this expansion parameter of this graph. And we also study this problem in a third model where we have this property that if we look at any subgraph within V minus S, its average degree is slightly less than D. So it is less than gamma D, you can think of it as some smaller than D. And this is true for all subsets of such V prime. So we also study our problem in semi-random models, the last two models. So to summarize, how large the G has to be so that the recovery problem can be solved? And this is the basic question which we try to answer. Our algorithm, which I will not be able to talk in this presentation, but it is based on rounding a semi-definite programming relaxation of the DKS. We show that the vectors corresponding to the planted set S are clustered together in space, and then we use some standard ideas from geometry to recover a part of the planted set, and the rest of the planted set can be recovered using some greedy algorithm. So basically algorithm based on rounding SGP relaxation, and once we have a part of the planted set, the rest of it we use some greedy tuning and so on. So these are some of the selected references of the paper. I'll just pause here for 10 seconds, and uh, that is pretty much it from my side. So if you have any
Yes,
questions.
thank you very much, Yash. Any questions?
Yes, thank you. Just could you elaborate a little more? So I'm interested in geometry in general. Like you said, you use ideas from geometry. Could you elaborate a little more? Or?
So the idea is to so SGP. What does SGP essentially do is like sort of convert our problem into a high dimensional geometry problem, right? So we have a vector corresponding to each vertex. So in this higher dimensional space, we have these vectors with some special properties from the constraints of the SGP. So how do we use those to, and now let's say we somehow know that the vectors corresponding to S are clustered. So now we can use some small balls around each vertex and find that most of the vectors of S are in that ball.
Okay, thank you.
Any other questions? So one question I had is, so the second and third model, actually two questions. Right? So second and third model that you spoke about, what are you assuming in the cross edges? Should it be monotone or should they adverse? It has to be?
So the cross edges are both random in both the cases.
Okay, so that's like a fit with probability P kind of thing.
Yeah, that's a fit probability P. Adversary in all the cases is allowed to modify anything outside S.
I see. Okay. And do you know anything about spectral algorithms for these models? Like, do you know that they may not work, or do you have any sense of whether they may work?
So our algorithms, like generally these spectral algorithms are not very like not robust in the sense that they are not very good with dealing with adversaries. So
I see.
though these models have not been studied using a spectral approach, but Yeah.
I see.
Yeah.
Okay, great. Any other questions? Okay, so if not, we'll thank Yash again and maybe set up Poly for the next talk. And maybe again, like we'll wait for 2 minutes and then start.
I'm just going to share my screen now.
Perfect, perfect, yeah.
Can you see my screen now?
Yes.
Lovely.
Okay, maybe we can start. So the next talk, the last talk of this session is on faster property testers in a variation of the bounded degree model. And it's by Isolde Adler and Polly Phi. And Polly will be giving the talk. Apologies for mispronouncing any names in this session.
Thank you. So in our paper, we introduce a new property testing model, which is a variation of the bounded degree model. So I'll just give you a bit of an overview of this model and some results in this model today. So before I start, let me just give you an introduction to property testing in case you're not familiar. So our aim is to analyze the structure of graphs efficiently. So we might want to try and find out if a given graph has some global property or not. So is it connected or is it disconnected? And of course, we want to do this as quickly and as efficiently as we can. So traditionally, efficiently means algorithms that run in polynomial time. It's a polynomial in the number of vertices in the graph. But what if the graph is huge? So maybe it's so large that it's not even feasible for us to read the whole graph once. And therefore, even linear time algorithms that we know are too slow and we cannot run for this graph. And we know that these large graphs do appear in practice, for example, in biological networks and social networks. And so for these graphs by efficient, what I mean algorithms that run in sublinear or even constant time. Now, of course, to achieve sublinear running times, we're going to have to sacrifice some accuracy because we can't read the whole graph once, okay? And so property testing, it's a framework which allows us to develop these super efficient algorithms whilst providing probabilistic guarantees on the quality of the output. Okay, so let's say we have some set of possible inputs, and then we have a property on these inputs. Now, normally you want to try and decide exactly whether a given input has the property or not. In property testing, we relax this slightly, and we define a distance measure from the inputs to the property. And so in property testing, rather than trying to decide exactly whether an input has the property or not, we aim to decide with high probability correctly whether the input has the property or if it's far away from having the property. And if it's close to having the property, so if it's within these two circles here, we don't mind what we output. And there's various different property testing models which have been studied, which are all suitable for different types of inputs. So for example, there's the bounded degree graph property testing model, which, as the name suggests, is suitable for bounded degree graphs. And this is the model which our model is a variation of. So let me introduce this model first. So in the bounded degree property testing model, the input class is just some set of bounded degree graphs. And then we define a property on that class, which is just a subset of the input class. And then, as I mentioned before, we need to define a distance measure from graphs in C to the property P. So let's start by defining the distance between two graphs. So in this model, we say that the distance between graphs G and H is the minimum number of edge modifications which are needed to make G and H isomorphic, where an edge modification is just adding or removing an edge. Then we say that a graph is epsilon close to the property P on C, where epsilon is just some small number between 0 and 1. If there exists a graph H which has the property such that the distance between G and H is at most epsilon times D, where D is the degree bound, times the number of vertices of G. And this is essentially just an epsilon fraction of the total possible number of edges in the graph. We then say that G is epsilon far from P if it's not epsilon close. An epsilon tester is then a probabilistic algorithm which is given oracle access to a graph G from the input class C, and it's also given the number of vertices of G. The epsilon tester then accepts G with probability at least 2/3 if G has the property, and it rejects G with probability at least 2/3 if G is epsilon far from the property. Now, if you notice, the epsilon tester is given oracle access to the graph G rather than G itself. So depending on what model you're in, the testers can make different types of queries to the oracle. But in this model, the tester can ask for the ith neighbor of a given vertex in the graph G, and then the oracle will return the ith neighbor in constant time if it exists. If the vertex in question has less than I neighbors, then it will return a special symbol to indicate this. And we assume this can be done in constant time. So the query complexity of a tester is the maximum number of oracle queries which are made with respect to n, where n is the number of vertices in the graph. And we're interested in making sure that the query complexity of our testers is as small as possible, because if we have good query complexity, then we're likely to have good running times, okay? So we say a property P is uniformly testable on the input class C if for every epsilon between 0 and 1, there exists an epsilon tester for P on C, which has constant query complexity. And this tester must work for any size graph. And then, as usual, the time complexity of the testers is with respect to n, the number of vertices in the graph. Okay, so now let me discuss our model. So our model, as I mentioned before, is a variation of the bounded degree property testing model, which I will refer to as the classical model from now. So our model differs from the classical model in two ways. So firstly, in our model, the distance between graphs G and H is now the minimum number of edge and vertex modifications which are needed to make G and H isomorphic. So if you remember back to the classical model, we only allowed edge modifications. So now we can compare graphs on a different number of vertices. And then secondly, we now say that G is epsilon close to the property P on input class C if there exists a graph H which has the property where the distance between G and H is at most epsilon times D times the minimum number of vertices in G and H. So let me just look at a quick example demonstrating the differences in this distance measure. So here we've got two graphs, G and H. So in the classical model, the distance between these two graphs is infinity because we can't make them isomorphic with only edge modifications because they're on a different number of vertices. Whereas in our model, the distance is 1 because we can just remove a corner vertex from G to obtain a graph which is isomorphic to H. So one of our first questions when studying this model was, how does it compare to the classical model? And it's fairly easy to see that any property that's testable in the classical model is also testable in our model with the same time and query complexities. So any results from the classical model carry over to ours. So our next question is, well, is the converse true or not? So are there properties which are testable in our model, but are not testable in the classical model? And we do find such a property. So we find a property on the class of all bounded degree graphs, which is testable in our model, but not testable in the classical model. I won't go into details about this property now, but it is in the YouTube talk. So this is nice. So this tells us that our model is actually stronger than the classical model in the sense that every property that's testable in the classical model is testable in our model, but the converse is not true. Another interesting question is, are there properties which are testable in the classical model, but can be tested with better running times in our model? And in 2018, Isolde Adler and Frederick Howarth, they show that every property that is definable by a monodic second order logic with counting sentence on the class of all bounded degree and bounded tree width graphs is uniformly testable on that class with polylogarithmic running time in the classical model. Now, we don't actually know if this can be improved to constant time or not, but in our paper we show that in our model it can be improved to constant time. But as I said, we don't know if this is an actual improvement or not, but it would be very interesting to know. So let me just conclude with some future work. So we'd like to identify other properties which are testable in our model that are not testable in the classical model. So if you have seen the YouTube video, you'll know that our property that we give, which is testable in our model but not in the classical model, it's not a very interesting property and it's trivially testable in our model. So it'd be nice to find a property which is testable in our model but not necessarily trivially testable in our model, and which of course is not testable in the classical model. And as I've just mentioned, it would be nice to know if properties expressible in CMSO on graphs of bounded degree and bounded tree width can be tested in constant time in the classical model or not, as this would tell us if our result is an actual improvement. So do we get a property which is which can be tested more efficiently in our model? And then finally, as with any property testing model, it's always an interesting question to obtain characterizations of properties that are testable. Now, this is a very difficult task. That maybe a good starting point would be to look at a known characterization in the classical model and see if this carries over to our model. So of course, one direction will, because we know that every property that's testable in the classical model is testable in our model, but does the other direction carry over also? So thank you, and if you've got any questions, I'm happy to take them.
Thanks, Polly. Any questions?
May I ask one?
Sure.
So I'm not within property testing, so sorry about that. But
That's fine.
From a general point of view, you seem to consider the space of degree-bounded graphs as a superclass. What would change if you go or if you switch over to bounded average degree instead?
Yes, so there are multiple different models. So there is a model which is suitable for general graphs, which will probably cover the bounded average degree. Now that model, it's not as well studied as the bounded degree model. So it's, by taking away the bounded degree, you sort of lose some of the techniques that you can use. So a lot of the techniques we use when we've got bounded degree is we know we can compute the neighborhood type around a vertex in constant time, so we can explore a local fixed radius neighborhood around a vertex in constant time. But if you remove that bounded degree, then you can no longer do that. So it becomes a bit more difficult.
Yeah,
there is also a lot of work for, sorry.
With bounded average degree, I would assume that at least in some probabilistic sense, you still have some properties like that.
Yeah, you can. It's just, let's say there are some results, but it's just not as well studied. So, I mean,
I'm asking this because your very first motivation was because, okay, you cannot load big social graphs or whatever into memory, but usually they tend to have a bounded average degree. There might be large degree vertices, but only few.
Yeah. So, I mean, I don't know off the top of my head all the results for average degree. I mean, there are some, but there's just not as much as for bounded degree. And there is a lot of work for dense graphs as well, which is a lot better understood.
Yeah, okay.
But average degree, there's not that much known, to be honest.
Okay, thank you.
So, sorry, I can't answer that any better.
No, fine.
Yeah. Any other questions?
Yes, I have actually. I'm also not into this property testing. Sorry, so maybe my question is stupid, but it just, you said like your model is more powerful, like because you can test some more properties. But in a way, like, well, I don't remember how exactly you said it, but also like the queries you can test and what you can do. Like if I wanted to somehow implement that, this would take more. Like I don't know, like I'm not sure I understand what you mean, like when you say that in a way it's stronger, because also in a way you need to be able to do more things, and of course you're paying that somewhere else. Like your oracle is more powerful, but you need to pay for that.
I mean, so when I say that it's stronger, just that it allows more testable properties. I mean, we don't really know how many what properties they are, which are testable in our model that are not testable in the classical model. So the example of the property that we give, it's not a very interesting property, but I wouldn't say that you have to do more work. So if you were going to look at an example of a property tester, normally what they do is they sample a constant number of vertices from the graph and then explore around those vertices, and then based on what it sees, it tries to decide. So the algorithms are actually very simple. It's normally in the proving correctness, which you get the difficulty. And so when you're proving correctness, allowing the removal or addition of vertices, it makes it actually a bit easier to deal with in a way. In certain cases anyway. If that answers your question. Or...
So I think also my question was kind of, but maybe it's stupid. It's just like, if I look from what you said at the beginning, like I have a huge graph and I want to do things with it. And here, if I understand correctly, you have like your oracle is more powerful. But in the end, if I really want to do something with my huge graph, if my oracle is more powerful, I need somewhere to spend more time with this oracle.
So so in our model, we allow the exact same oracle queries, so we don't change that. It's just the distance measure. So from the actual algorithm's point of view, it doesn't really, it's not going to do anything differently. It can't ask different questions or anything like that. It's just that different graphs will be classed as close and far in each model. That's the difference.
Okay, thank you.
Any other questions? Okay, if not, we can thank Polly and also thank all the speakers of the session for great talks. I guess there's going to be a break for 20 minutes, so we can reconvene in the same links in 20 minutes time for the next session. And thank you for joining this session.
So do we have the speaker for the first talk? Omar, Wasim, and Valerie King.
Yeah, I'm right here.
Thank you. And then we have either Nikhil Mande or Swagato Sanyal. So Nikhil, will you be speaking?
Yes.
Okay, thank you. And for the third talk,
Anna is here.
you're
It's
here?
a long sequence of photos. Yeah.
Okay, great. Thank you. Okay, and the next we have Niels Moravich, Niels Christian Komovich, and Frank Sommer. Fair Cut Games. Or Niels Moravich is here, so probably. Hi, Niels. Okay, great. Thank you. Okay, and for the last talk, Kishore
Can you hear me?
Katapale. Yes.
Oh, okay, perfect.
I'm here, Shreyas.
Shreyas. Okay, thank you. Okay, so I now request Omer to share his machine and or the file.
So I think you'll have to allow me to share the screen because currently I cannot share my screen.
Okay, let's see if I have a permission to share. Yeah, you're co-host now, so you should be able to share your file now.
So is my slide visible to all of you now, or is...
Yes, it is visible.
Okay.
Okay, so all of you know that there will be at most 10 minutes of your talk, and there will be or 8-9 minutes of your talk, and then there will be a question answer. So let's try to stick to the time in everybody's interest. Okay, so someone told me that my background was looking terrible, so I've changed my background to slightly better, some saner background. So we'll wait for a couple of more minutes, and then we'll start. Okay, so welcome to all of you for this session of FSTTCS. So the first talk in this session will be fully dynamic sequential and distributed algorithms for MaxCut. And the talk will be given by Omar Masim from Northwestern University. Omar, floor is to you.
So hello everyone, welcome to my talk. Thanks for coming to my talk. Today I'll be talking about free dynamic algorithms for MaxCut, and this is joint work with my master's supervisor Valerie King, who's at the University of Victoria. I'd like to dedicate this talk to my father, who unfortunately passed away last week due to COVID-19 complications. So let me just start with the basic definition of the max cut problem. So given an undirected, unweighted graph, we want to find a cut, which is just a partition of vertices into two parts, S and S bar, such that the number of edges between S and S bar are maximized. In this picture on the left, you can see the green edges, which are the cut edges, and the pink edges, which are the non-cut edges. And you want to find such a partition. And max cut is one of the most well-known NP-hard problems. In fact, we cannot obtain an approximation which is better than 0.878 under the Nikam's conjecture. So all what we can hope for is an approximation algorithm, and more precisely, a T approximation algorithm is going to return a cut, which is just a partition of vertices, such that the number of cut edges is at least a T fraction of the optimal number of so it's a T fraction of the optimal number of edges. Here, the optimal number of edges refers to a cut of which has the maximum number of cut edges. So I would like to make a distinction here between respecting cuts versus approximate cuts, since all algorithms in this paper actually obtain respecting cuts. So we say that a cut is T respecting if the number of cut edges are a T fraction of the total number of edges. So this trivially implies that a T respecting cut is always a T approximate cut, because the number of edges E is actually an upper bound on the total number of cut edges contained in any cut. But however, a T approximate cut, the difference in the number of cut edges between a T approximate and a T respecting cut can be actually equal to a constant fraction of the total number of edges for certain graphs, such as the complete graph on 2n vertices. So some known results in the static setting include Johnson's half approximation algorithm. Actually, it yields a half respecting cut. The state of the art is a 0.878 approximation due to Comans and Williamson, and a matching on almost optimal approximation is obtained by a primal dual algorithm of Aurora and Calle. And we also have some spectral algorithms, but here we note that Johnson's greedy max cut is actually, in fact, the only algorithm that gives a half respecting cut in linear time. So the greedy max cut algorithm simply starts with an arbitrary ordering of the vertices, and it considers each vertex in that order and adds the vertex to the side of the cut, which has the fewer of its neighbors. This ensures that at least half of the vertex's neighbors are adjacent in the cut. So this is a linear time algorithm. It gives a cut which has at least a half fraction of all the edges in the graph. Since this talk is about fully dynamic algorithms, let me just give you a feel for what they do. So initially we have an empty graph on, let's say, n vertices, and at each time step we have an edge insertion or an edge deletion in the graph. And so you can see we have an arbitrary sequence of edge insertions and deletions, and after each edge update, we want to maintain a property of the underlying graph. And the goal of a fully dynamic algorithm is actually to maintain a property faster than we can use, or we can invoke the best static algorithm. And most commonly in this area, we have problems which already admit polynomial time static algorithms. But starting with the seminal work of Onek and Rubenfeld, people have started studying problems which are NP hard. And in this context, we want to maintain the approximation we want to maintain a certain approximation to the graph under edge updates. So in the context of this max cut problem, we start with an empty graph on n vertices, and we would like to maintain a half respecting cut, a cut which contains at least half the number of total edges at any given point under edge insertions and deletions. So as you can see, we are revising this cut periodically after every edge update. to the graph. So we would also like to answer these queries, such as whether an edge is contained in the cut or not, the total number of cut edges maintained at any given point, and the size of the vertex partitions which define the cut. Here we would like to maintain at least a half respecting cut. So we could actually obtain fully dynamic algorithms by using known static algorithms by simply using a static algorithm and periodically rebuilding the data structure from scratch. Here we would only use lose epsilon in the approximation, and we can sort of get a worst case update time. So the proof of this lemma is actually in the original paper. But if we do this, we actually do not get sublinear update time using the best known static algorithms for maxcut. In fact, if we want to obtain a half respecting cut, we can get an update time which is at least omega of n. So the goal of this paper is to actually bridge this gap and actually get dynamic algorithms which get sublinear and sublinear update times. So we obtain the following results. So the first algorithm actually is very simple, and this is actually used as a black box for all the other algorithms which we obtain in this paper, and most likely I'll just have time to go through this simple algorithm. So we look at two updates which are sort of the relevant updates in this setting. So the first update, which might potentially lead to a cut falling below half respecting, is an insertion of a non-cut edge and a deletion of a cut edge. And the main observation that we make is that if a cut is actually not half respecting, then there should be a vertex which, if we move from one side of the cut to the other side of the cut, then the cut will actually increase in value. So this vertex is sort of called a switching vertex, and in this algorithm, in this diagram, you can actually see that these red vertices are the switching vertices because they have, so if you move any of these vertices to the other side of the cut, then this would actually increase the number of cut edges. So the algorithm simply just maintains a set of switching vertices, and after every edge update, we would, if the cut is no longer half respecting, then we switch this vertex. And the simple reason why there should exist a switching vertex is because if not, then every vertex would be incident to at least half its neighbors, and the cut would already be half respecting. So this is a very simple algorithm. We simply maintain a set of switching vertices. If a vertex is switched, we update all its neighbors. This yields an O delta update time. And actually, the switching vertices are not necessarily the endpoints of the updated edge, so we cannot actually sort of save or look at a constant. We can't look at a constant neighborhood, constant radius neighborhood of the endpoints of the updated edge to find a switching vertex. So this algorithm actually generalizes in the MPC model, and it gives us an algorithm, a fully dynamic MPC algorithm, which is able to handle an update in constant rounds, delta messages, and the adjustment complexity is just constant. Here, the adjustment complexity is just the number of changes to the maintained cut. So if you want to update sublinear update time in the sequential setting, we note that for large delta, the update time can be as much as O of n, which is no good. So the two main techniques that we use to improve this update time beyond delta is that we partition G into vertex disjoint induced subgraphs. We separately maintain half respecting cuts on them, and then we combine those cuts. But to do this, we would additionally need to maintain these edge counts between those respecting cuts that we obtain on those two vertex disjoint induced subgraphs. So the main idea behind the square root m update time algorithm is just to maintain half respecting cuts on low and high degree vertices, which are simply defined by this threshold square root m. So if a vertex has degree square root m or less, it's a low degree vertex, otherwise it's high degree, and so on and so forth. So I wouldn't have time to go through this algorithm, but the last result that we obtain is a randomized algorithm, and it generalizes the idea of cut combining to a random partition of k vertex disjoint induced subgraphs, which have roughly equal size, and we can then combine the cuts on all of those k subgraphs to get a global cut for G. And this actually gives us a sublinear update time of n to the 2/3 with high probability. However, this only holds for an oblivious adversary, in that the adversary fixes the whole sequence of edge updates in advance. So I'd just like to go through some open problems. So here in this work, we get a fully dynamic algorithm, MPC algorithm with delta messages. However, we are using a total of n machines, small n machines. But the main open problem is whether we can get a square root of n total machines. Here capital N actually denotes the total number of vertices and edges in our graph. And we would like to get a fully dynamic MPC algorithm with square root of n total machines and square root of n memory per machine, with almost constant number of rounds and active machines. And one of the main open problems is to improve the update time beyond square root of m in the sequential setting. And the sublinear update time algorithms that we obtain in this work actually have a large adjustment complexity, and one of the major open problems would be to actually reduce this adjustment complexity. In the static setting, the best known algorithm that we know to compute a half respecting cut actually uses almost delta rounds in the congest model, and this is a very natural open problem which arises from this work. So you'd like to get a small O of delta round complexity in the static congest model. So again, thank you all for coming to this talk, and I'd be happy to take any questions that you might have.
So thank you, Omar, for such a nice talk. I think we will find a time for one quick question if anybody has. Either you can ask a question directly by unmuting yourself or writing it in chat. So I don't see any questions then. Thank you, Omar, and I will move to the next speaker. Nikhil, could you share your slides?
Yeah.
Thank you, all. Thanks.
Thank you, Omar.
Is it visible? Are my slides visible?
Yeah, your slide is visible. Okay, so all set. Can I announce, Nikhil?
Sure.
Sure. So the next talk will be on parity decision trees for Fourier sparse Boolean functions. And this is a work by Nikhil and Swagato, and the talk will be given by Nikhil. So floor is to you, Nikhil.
Thanks, Akhil. Yeah, this is joint work with Swagato Sanyal, who's at IIT Kharagpur. And this is work done while I was a postdoc at Georgetown University, and I'm currently at CWI Amsterdam. And I just realized the date is wrong. Apologies for that. Thanks for attending. Okay, so the first few minutes, I'll try to explain what Fourier sparse Boolean functions are. After that, I'll try to explain what parity decision trees are. And then I'll spend a little time telling you why we care about parity decision trees for Fourier sparse Boolean functions, after which I'll be able to sketch our main theorems and some conclusions. Okay. So the relevant functions to define Fourier analysis of Boolean functions are those with domain f2 to the n and range reals. So for any n-bit string alpha in f2 to the n, we define an associated character or parity as follows. On input x, pick out the xi's for those I where alpha I is equal to 1 and count the number of ones there. If the number of ones is even, output 1, and if it's odd, output -1. So there are 2 to the n such functions. And it's a well-known fact that every function of this form has a unique representation as a linear combination of these parities. Okay? And in this representation, the coefficients are called the Fourier coefficients. And this representation is called the Fourier expansion of f. Now, in particular for this talk, we'll be interested in those functions where the range is -1, 1 or Boolean valued functions. Denote the Fourier support of f by calligraphic S to be the set of all characters or parities whose corresponding Fourier coefficient is non-zero in the Fourier expansion of f. And we're going to use k to denote the Fourier sparsity of f. That's the cardinality of this set. Okay, so that's Fourier analysis of Boolean functions, a very quick primer. What are parity decision trees? Parity decision tree is a model of computation of Boolean functions. So in this figure, this takes as input a 4-bit string and outputs a value in -1, 1 as follows. First query the parity of the first 2 bits, x1 and x2. If it is 0, go to the left subtree. If it is 1, go to the right subtree and iterate until you hit a leaf. And when you hit a leaf, output the value at that leaf. Okay, so this naturally computes a Boolean function. The internal nodes are parities of subsets of variables. And the parity decision tree complexity of a Boolean function f is defined to be the minimum depth of a parity decision tree that computes f. Why do we care about parity decision trees for sparse Boolean functions? Here's a trivial upper bound. Parity decision tree complexity of f is at most k. Recall I'm using k to denote the Fourier sparsity of f. Why is this? Just write out the Fourier expansion of f. Query all of the parities that are in the Fourier expansion. Once you have the answer, just plug it back into the Fourier expansion and you know the value of f. And the reason we care about upper bounds for this is that it has connections to communication complexity. By a recent result of Hatami, Hosseini and Loveth, it turns out that proving upper bounds of parity decision tree complexity of f of the order polylog in k, note that the trivial upper bound is k, this is equivalent to resolving the log-rank conjecture for XOR functions. I'm not going to get into more detail now, but the log-rank conjecture is a very well-known open question that's still open in communication complexity. And the best progress towards this is a result due to Sang, Wang, Xie, and Zhang from 2013, which is order square root k. So as you can see, there's a big gap left between square root k and polylog k. So our first result is we're going to give a reproof of this result in hope that some of our techniques can hopefully progress towards proving better upper bounds. So let me tell you about the result of Sang et al. And there was also a result by Spilka, Tal, and Volk that appeared concurrently around the same time, which had quantitatively weaker results, but essentially the same ideas. So Sang et al. First show by a careful argument that there is a leaf of depth order square root k. What does this mean? That means there's a set of order square root k parities such that when you query them, given any Boolean function, of course, such that when you query them and get a particular set of outputs, in this case, that is, if you query x1 plus x2, get 0, x1 plus x3, and you get 0, then the function is guaranteed to be a constant. So this is the first step. The second step, the second claim is that if we have such a leaf, then all the other leaves, the sparsity must have halved of the restricted function. So on this leaf, the sparsity of the restricted function is 1 because it's a constant. And on all other leaves, the claim is that it halves. And this step requires a careful argument and a careful choice of parities. And now you see, you can just iterate this argument at each leaf and you get a recursion for the depth of the tree that you obtain, which is order square root k, a recurrence. So now let me tell you where our work differs from theirs. As you can see, the figure is slightly different. So we bypass this step of finding an affine subspace where you make f a constant and directly argue that there exists a set of square root k parities such that on being queried, the sparsity of all these leaves are halved. And we don't even need to choose carefully a set of order square root k parities. We show that a naive sampling of parities from the Fourier support of f suffices to do this. So this is the main step where we differ. And the same recurrence still holds, and we get an upper bound of order square root k. And what's the key insight? What's the key technical tool that we use? There's this notion of equivalence classes on pairs of elements in the Fourier support of f. A pair is equivalent to another one if the sums of their elements are equal. This plus is over f2 to the n. And the crucial observation is that suppose I query gamma, right? Then no matter what the outcome is, 1 or minus 1, or 0 or 1 in this case, alpha 1 and alpha 2 get identified with each other. That is, the sparsity of the initial function drops by at least 1. Let's illustrate that with a simple example. Suppose the original function had this Fourier representation, and you queried the parity x1 plus x2. Note that no matter what the value of x1 plus x2 is, these two terms get identified because x1 plus x2 is set to a value, constant, 1 or 0. Similarly, these two terms get identified. So the sparsity of the resulting function drops by at least 2. So this is now our goal. Find a set of gammas such that they correspond to really large equivalence classes in F. And the key tool we use is a proposition of Titsworth from 62. It's not that hard to prove. In fact, all equivalence classes have size at least 2. And going beyond that, we have a conditional improvement. If we say that if a large fraction of equivalence classes that's captured here have large size that's captured here, then we get an improved upper bound on the parity decision tree complexity of F. So in particular, this recovers a reproof of the order square root k upper bound, but up to a log factor in this case. Finally, now, why do we even expect this to be true? We ask that question. Can it be possible that Titsworth's conditions are tight? That is it possible that there's a Boolean function for which every equivalence class has size exactly 2? And this is our next contribution. We say, no, this is not possible. In fact, we have something slightly stronger. For every alpha in the Fourier support of F, there must exist another beta such that alpha plus beta has equivalence class size at least 3. That is, every element participates in an equivalence class of size at least 3. And we have some sort of a tightness result for this as well. In summary, we reprove a result from Sang et al. That shows that parity decision tree complexity of F is order square root k. And we show that we can do so by just sampling parities at random iteratively. We give a conditional improvement upon this based upon an improved folding property of Boolean functions, if it holds true. Towards this, we show that Boolean functions indeed do have non-trivial folding properties. There exist equivalence classes of size larger than 2. Finally, we have a conjecture that says that's significantly stronger than the result we have here. That says every Boolean function is delta comma half plus half minus little o unfolding. So in particular, this would imply the following upper bounds on parity decision tree complexity. It would also give some upper bounds on communication complexity, which would improve upon best known upper bounds due to low weight. Thank you.
Thanks a lot, Nikhil, for such a wonderful talk. So do we have any questions for Nikhil? So there doesn't seem to be any question, Nikhil. So let me thank you again for such a wonderful talk. Let me clap for you. And so I invite next Anna to share her slide, and we'll wait for a few minutes because we're still early, we have time. So let's get ready.
You please allow me to share screen.
Are you not a co-host? Yeah. Yogesh, could you make Anna a co-host? Can I make you a co-host? Let's see. Yogesh, please make Anna co-host.
Nothing happens.
I'm sorry, Anna, I don't have permission to make you co-host.
That's
Only
fine.
Yogesh can.
Saket, if you cannot, I don't think Yogesh can, because both of you are just co-hosts. So you need.
So maybe Track A, FSTTCS.
Yeah, right. Yeah.
Yeah, he's calling the person
I
who
see
will
here.
host.
Wow.
Yeah, I think now you're co-host.
Be able to see my screen? Yes, so let's start. Now I'd like to.
Just 1 second, I'll introduce you. Okay. I think it's now time. So next talk will be on fair tree connection games with topology dependent edge cost. It's a joint work with David Bülow, Tobias Frederick, Pascal Lengner, Anna Melenstokin, Loz Molitor, and the talk will be given by Anna. I'm sorry if I didn't take your name properly. Difficult.
That's fine. Thank you for
Thank
the
you.
introduction. So I can probably then skip this part. And let's go to definition of the game. So our game, we consider, takes its origin from so-called fair single source connection game, which was introduced by Ancelevich et al. Roughly 10 years ago. So here we have a set of key players and a given weighted directed graph, and all players can buy edges to connect the terminal with a common target. They fairly share cost of each edge, and the aim is to minimize cost of the entire path. The problem is the problem of this game is when we try to apply it for some real-world situations, like, for example, wireless devices who want to send the energy or the message to a common target. Usually, the devices cannot observe and pick edges from the entire network. In the real world, it's more local. So in this direction went another model, so-called selfish spanning tree game model, where agents are nodes. So each agent is collocated with exactly one node of a network, given weighted network. And again, agents want to connect itself with a common terminal. For doing this, they are allowed to pick one neighbor to connect with, and after establishing a connection, they connected by path to the common target. And the aim is to maximize utility, and utility can be computed in 3 different ways, as authors define in the paper. For example, it can be a bottleneck of the path. For example, here the bottleneck is 5, so both agents, agent I has to pay 5, and agent J has to pay 3 because the bottleneck is 3 on the way to the root. Or it can be minus or plus weight of the established connection. But we decided to go further and somehow combine these games and add a new ingredient. It's topology-dependent edge cost. Namely, we are given a set of n agents and one special node, which is a root. All agents, again, are nodes of a network. Network is unweighted and directed. Directed, and each agent wants to connect with a common target. To do this, they are allowed to pick only one neighbor to connect with. And after establishing a connection, each agent has to pay the cost of the entire path, where the cost of the path is calculated as follows. So it's total cost of all edges, where each cost is, first of all, depends on the topology, so it's proportional to the in degree of its endpoint, fairly divided by all its users. So by all its users, we mean, of course, a subtree rooted in the corresponding node. So for example, for this edge, its cost will be 2/3 because it has in degree 2 and it has 3 users. So this subtree set is exactly a set of users of this edge. So the next one is 3/5 because it is in degree 3 and has 5 users. And each player seeks to minimize the cost of the entire path and to be connected with a common target. And the main goal of each game and of our game is to understand what is a stable state of the game, namely what is a pure Nash equilibrium of the game. We call a strategy profile or a tree pure Nash equilibrium if no agent has an proven move, meaning that no agent wants to deviate from its current strategy, assuming that all strategies of all other players are fixed. And the corresponding questions are how does the stable state look like? What structural properties of the obtained stable tree or stable trees, and how efficient or inefficient this tree is, which is usually measured by the price of anarchy, which is the ratio between the total social cost of the most expensive Nash equilibrium we can obtain for a given number of players in comparison with the social cost of the optimum. By the optimum, we mean centrally designed network, designed by a central authority, which aims to minimize the average cost of all players. So the average cost is modeled as a social cost or the total cost of all players. And yeah, probably I have no time to go into details, but I can briefly introduce all main results, most of my main results of our paper. So our main focus, as I said, was to understand how the stable state looked like. And we observed many interesting properties. For example, we obtained an upper bound on the depth of the tree, which is this fancy ratio. We also observed that decrease sequence, so if we go from a leaf to the root, monotonically increasing, and also it cannot increase faster than 2 times in degree of previous node in the sequence +1. With all the knowledge combined, we were able to obtain the upper bound and lower bound in the degree of the root, and some other dependencies and observations you can find in our paper. Another interesting result is a constant trace of energy, which means that the network obtained by this decentralized strategical behavior is actually efficient in comparison with network obtained by some central authority, designed by some central authority. So it's at most social cost of any stable network is at most 8.6 times social cost of the optimum. Unfortunately, we proved one negative result, which states that stable state not always exists, and it exists, and we conjecture that it exists for infinitely many number of agents, but unfortunately not for all. And to provide this result and to support our conjecture, we discovered a class of balanced trees. I hope it's clear what balanced tree means. And we proved that balanced trees are always stable. So since we were able to provide this result for any n, it means that for infinitely large number of players, we can conjecture that stable state always exists. I think I can briefly, so in our paper, there is a huge section dedicated to extensions and generalization of our model, which are also interesting. First of all, it's a multi-target connection game. So when we have not only one root or one source to connect with, but many sources, but in this case, it's intuitively holds that it's just the game will be a combination of games played on subtrees. So the stable state is a forest of stable trees. And another interesting modification is a path version, which is closer to the original phase single source connection game, where agents pick not one edge to connect with root by the obtained path, but they pick the entire path in the network. And interestingly, that our game with single edge, where agents can pick only single edge, is a subset or subclass of path tree connection games. This extension. Yeah, the more results briefly obtained you can find in our paper. I think I will stop now and say thank you for listening.
Thank you very much, Anna. So we have enough time for questions. So I had just one quick question. So like, so did you also consider some computational aspects of these questions or just the existence?
For example?
Like computing, like, so when you say that this path TCG exists, then, so like, do you give an algorithm to compute these things or you just give a proof that these things exist?
Compute a stable state is easy because strategy for an agent is only one neighbor. So agent needs to pick only one neighbor to connect with. So it can be done by Kride algorithm in polynomial time trivially. Another problem, how fast it converges to a stable state, of course.
Yes.
And unfortunately, we showed a negative result. So there is a so-called improvement response cycle. It means that if we allow agents to be activated one by one, according to some activation order, they can come back to the original state. So, of course, it leads us to question the written equation, can we find some activation order such that we can guarantee converges to a stable state? But we show that it's not true in general if we allow some arbitrary activation order.
Okay, thanks a lot, Anna. So if there are no more questions, then let me thank you. And then I invite the next speaker, Niels, to share her slide.
Hi, Anna. I wanted to ask one question.
Yes.
Go ahead,
Hi.
Samyukta.
So the thing that you just explained to Sake, that you said that you get a cycle when you want to see whether it converges, the stable state. So does that mean that it cannot be done efficiently, or some potential function cannot exist by which you can reach the stable state, or it's just that this way of doing it is not correct?
It exactly means that there is no potential function. Okay. And yeah, but it doesn't tell that there is no way that it can be computed efficiently. As I said, that probably it's an algorithmic equation. Probably there is some way of computing a stable state, but we didn't pay too much attention to this question.
Okay. Okay, thank you.
Yeah, thank you. There was one question in chat, if I'm not mistaken, or not. So the question is there non-existent results also for pure Nash? Yes, all the results are for pure Nash. I use abbreviation Nash equilibria, but at the beginning I said that we always consider pure Nash, so discrete case, basically. Because it's easier usually to analyze than Nash equilibria, so we usually consider only pure Nash.
Okay, thank you. Thank you, Anna. So the next talk will be on colored cut games. And the co-authored by Niels, Christian, and Frank. And the talk will be given by Niels. Niels, floor is for you.
Thanks for the introduction. I hope you can hear me.
Yes, we can hear you.
Okay, good. So our paper is about the colored cut games, and I actually thought the talk were only 5 minutes, so might be a bit shorter than the rest of you. In our paper, we introduced the colored cut games, which is a family of defender-attacker games played on edge-colored graphs to model specific aspects of network security analysis. And in this talk, I just want to make sure you all understand the game rules of this game, and I only explain shortly what our results are, or the most important results. So, colored cut games, we have, as I mentioned, a edge-colored graph and two terminals S and T, and we have a defender who tries to connect S with T, so he tries to choose colors such that there's a path where the edge colors of this path are a subset of the colors he chose during the game. And on the opposite side, we have an attacker who tries to disconnect S and T by, well, preventing the defender from obtaining such a colored path. Let's start with the defender. He is allowed to choose only one color, and in this example, he has to choose the color red, as otherwise the attacker in the next turn can choose red and disconnect S from T. So the defender may choose red, and these edges are now secured. They cannot be destroyed by the attacker in subsequent turns. So now it's the attacker's turn. He, as I mentioned, tries to disconnect S from T. So he has to choose the blue color, as otherwise the defender can complete a path in his next turn. So say the attacker chooses blue, which can be modeled by removing the blue edges from the graph. And now it's again the defender's turn, and we can see that if he chooses the green color, then he can obtain such a path, which has only the colors red and green, and he wins the game. Let's make another example with the nice visualization, I hope you can see it, of some of our students who implemented these colored cut games. So again, we start with the defender. We try, these are the endpoints S and T. And let's say we start with the defender. He's allowed to choose one color, and you can see that this blue color is contained on all ST paths. So the defender has to secure this color, as otherwise the attacker would win in his next turn. So now it's the attacker's turn. And let's say the attacker now chooses the yellow color. Then these edges are removed from the graph, and it's again the defender's turn. And now we can see, okay, we have to choose this purple color in this turn, as otherwise the attacker again has a winning strategy. So we remove, we protect this purple color, and it's again the attacker's turn, and the attacker now has to choose the orange color, as otherwise, again, the defender could win in his next turn. Wait. So, and now we can see that these two vertices are in different connecting components, so the attacker won the game and had a winning strategy on this example graph. So this is not all about the colored cut games. In general, they are defined the following way, that they generalize two famous, or not only two, but many famous problems that were used and well analyzed in the past to model specific aspects of network security analysis. And so the budget are not one in each of the turns. So we have budget vectors. So we have, first of all, I turns. Each player has a budget DJ in his J's turn. So the defender is allowed to choose DJ many colors in his J's turn, and the attacker is allowed to choose AJ many colors in his J's turn. And there's only one other rule, namely that the players are not allowed to choose previously chosen colors. And as I mentioned, the goal of the attacker is to disconnect S&T, whereas the defender tries to connect S&T. And we were able to show that these colored cut games are p-space complete if this number of alternations between the agents is not a constant, even if the game I explained earlier, where the agents have only one, are allowed to only choose only one color at a time. So even in this case, and in very restricted instances, this problem remains p-space complete. But if the number of alternations is a constant, then we're able to show that these problems are complete for the 2i level of the polynomial time hierarchy, which is, well, still pretty bad, since it is unlikely to solve any of these games in polynomial time, unless we have a constant number of colors in the whole instance. But that's not all. We were also able to show positive results for the colored cut games, which I, well, just, I just explained it briefly. From a parameterized point of view, we were able to show polynomial kernelization algorithms for all colored cut games, which is pretty nice, since even these basic colored cut games, which we generalize, namely the labeled path and the colored ST cut problem, did not admit polynomial kernel or known polynomial kernelizations so far. So the conclusion would be, we introduced these colored cut games, which are motivated by network security analysis, and we analyzed their complexity, showed their p-space completeness in general, and for a constant number of alternations, their completeness for the 2i level of the polynomial time hierarchy. And we also obtained positive results from a parameterized point of view. Well, it was shorter than expected, but if someone is interested, volunteer, or maybe two of you, you can play this game against each other right now. Thanks for your attention. Hope you enjoyed.
Thanks, Nils, for such a good talk. So if I may ask a question,
yes,
is that, so you said that you showed that the problem admits a polynomial kernel, but kernel with respect to what as a parameter?
It's a parameter combining structure of the graph and the budget of the attacker. So, okay, it's the longest path modulator, which is a generalization of the vertex cover number.
Okay.
Oh wait, I can show it. I have the root. Wait a second. Where is it? Where is it? Parameterized by kappa d, which is the vertex deletion distance to obtain a longest path, such that the remaining graph does not has a path of length d+1, and the budget of the attacker k. So in other words, if d is equal to 1, then we have the vertex cover number. So parameterized by the vertex cover number and the attacker budget, we obtain a kernel of size vertex cover squared times k squared.
Okay, thank you.
Further
I have
questions?
one question.
Yes.
Your game is basically a two-player game. Did you consider generalization to multi-commodity or multi-agent version? When you
Not
have
yet. Actually, yesterday I thought, well, how about a third player who tries to somehow intersect both of the goals of the attacker and the defender, but we haven't analyzed it yet, no.
I mean, it's also kind of close to this fair connection game I introduced in the beginning of my presentation, where each player has a pair of terminals to connect, and in combination with your game, I think it also can be useful to define models describing these COVID situations, because you have one connection, you want to keep this connection kind of stable, and you have one attacker can remove edges from your connection, and yeah.
So we have many
stable.
defenders who try to secure their
you have-
separate terminal pairs, and one attacker who tries to fight against all of them.
Exactly.
Yeah.
And to point out to another result, there was one paper 3 years ago, 4 years ago, about network creation game where one attacker was randomly removing one edge, and all players wants to keep connection with all other players, and also to minimize distance towards other players, and at the same time to keep this network connected after the attack. Maybe you're interested. Yeah.
Yes.
Thanks a lot for nice comments. We still have a lot of time, so if people have questions. So just as a side comment, so since you are able to bound this modulator and you're bounding the path of length d+1, then isn't like this is like a tree depth modulator?
Yeah, actually, this was a corollary from this result. We were also able to show is for tree depth modulator, but in this case, we would have a factor of 2 to the kappa d
here
squared, I guess. So it's not a polynomial kernel, I guess. Or wait, have to look it up. But we have a corollary looking for the tree depth modulator.
Okay.
Oh no, I know. In the exponent we have a 2 to the d, which is very impractical for any algorithm you would use, but it works. We also have this. So this result implies an tree depth plus k, tree depth modulator plus k algorithm. Kernel.
Okay. So did you try parameterizing something else other than these?
Yeah, we make a very wide view of parameters, like for example, the total number of colors. For the total number of colors, it always admits an FPT algorithm, but presumably no polynomial kernelization algorithm. For example, for only the budget, it is W2 hard, so there's presumably even no FPT algorithm. and even on constant degree graphs, all these problems are very hard.
Okay. Okay, so thanks a lot, and thanks a lot for such a good talk. So let me clap, and I enjoyed looking at your game. So now I request the next speaker to share his slide, and our next speaker will be Shreyas Pai. Shreyas?
Yes, so I think you have to.
Yeah, you're co-host, so you should be able to share your slides.
Yeah, so I think Niels had to unshare before I shared, so I can share.
Okay, now I can see your slides properly. Now it's gone.
So just a second. Okay, and now it's working.
Yes, now it's working. So let's just wait for a minute and then we can start because.
Okay.
So now we have the last talk of this session. The title of the talk is Sample and Gather, Fast Ruling Set Algorithm in the Low Memory MPC Model. And this is a joint work with Kishore, Shreyas, and Sriram. And the talk will be given by Shreyas Pai. Shreyas, floor is for you.
Thank you very much for the introduction. So let me begin the talk. So we talk about ruling sets in this paper. To define ruling sets, let me first define what a maximal independent set is. You're given an n vertex graph with m edges and maximum degree delta. And you want to find an independent set I such that every node is within one hop of some node in I. So let's look at that with an example. Here's this graph with orange vertices here. They form an independent set and every blue vertex is within one hop. And also note that the same holds for the blue vertices as well. So both of these sets form a valid maximal independent set in this graph. So we don't really care about minimizing, maximizing size or anything. We just want to find a maximal independent set. We can generalize this definition to beta ruling sets, where we want to find an independent set I such that every node is within beta hops of some node in I, and this holds for an integer parameter beta greater than or equal to 1. So the MIS definition we saw before is also a one ruling set, and it's also a beta ruling set for any beta greater than or equal to 1. So for beta equal to 2, both the MISs we saw in the previous example are valid two ruling sets, but also this single orange vertex trivially forms a valid two ruling set as well. So with these definitions out of the way, let me define the massively parallel computation model, which is the model that we look at. So this is a theoretical abstraction of modern distributed systems like MapReduce and Spark, and it was introduced by Karloff et al. In SODA 2010. And a main attraction of this model is that it allows all-to-all communication between the machines. So the MPC model is defined by a set of machines, each having a local memory parameter of S words. They get machines get an input of total size capital N, and if the input is a graph, this capital N will be the number of edges plus the number of vertices. And the local memory per machine is assumed to be much smaller than the input size. In particular, capital S is O of N raised to S delta for some constant delta between 0 and 1. So it's strongly sublinear in the size of the total input. And the communication goes in synchronous rounds. So consider the set of machines in round t-1, round t, and round t+1. So the machines in round t, they receive messages from the machines in the previous round. They perform some local computation, and then they send messages to the machines, then they will receive it in round t+1. The main constraint for this communication is that at a single machine, the total number of messages received and the total number of messages sent in any round is at most it's upper bounded by the local memory parameter capital S. So note that a single machine can actually send S messages to a particular machine in round t+1, but provided that the receiving machine also receives at most S messages as well. So for graphs, there are a bunch of memories in the MPC model that arise. Note that the local memory parameter is always sublinear in the total size of the graph. When we relate the local memory parameter to the number of vertices, you actually get three different regimes. The one is the superlinear regime, where S is superlinear in the number of vertices. This regime only applies for when your graphs are sufficiently dense. Then there is the near linear regime, where S is roughly linear in the number of vertices. And then there is the sublinear regime, where S is strictly sublinear in the total number of vertices. And we work in this sublinear memory regime in this talk and in this paper as well. So this this sublinear memory regime is also called the low memory MPC model. And when we look at two ruling sets in the low memory MPC model, let me compare it with the complexity of connectivity MIS and MIS as well. So using the result from Karloff et al., we can this is like we can show logarithmic round MPC algorithms for connectivity MIS and two ruling sets. So this is in fact a general simulation theorem for PRAM algorithms. So if your PRAM algorithm is not too crazy and satisfies some straightforward assumptions, you can simulate it round by round. So this gives us logarithmic round algorithms in this model. And in fact, for the reason I've put connectivity here is that it is widely believed in this model that log n is the correct complexity for connectivity. But we do not know any unconditional lower bounds yet. In fact, the best lower bounds known for connectivity are only constant. For MIS and two ruling sets, perhaps surprisingly, we can do much better than this logarithmic runtime. We can break the logarithmic barrier to get a square root log delta around algorithm. And here delta is the maximum degree. And in this work, we know that for two ruling sets, in fact, we can do a lot more better than what we can do for MIS. We show a log delta raised to 1/6 round algorithm. So the way we do this is by presenting sample and gather simulation theorems. And these general simulation theorems show us how to compute two ruling sets in log delta raised to 1/6 rounds, and more generally, beta ruling sets in log delta raised to some exponent, which is exponential in beta. So sublogarithmic algorithms in the low memory MPC model, like the ones for MIS in the previous work, they basically work by trying to quickly simulate an R round congest algorithm, where R is log delta with high probability. And the congest model is the classical model that I will briefly define in the next few slides. So we basically go from log delta congest rounds to square root log delta MPC rounds. So in the congest model is a synchronous message passing model, and you're given a graph G, which is also assumed to be the communication network. And the nodes can send log n bit messages per neighbor per round. And a very important feature is that all the computations are in fact done locally. So you can basically define the model from the perspective of a single node. So a single node in a synchronous round, it will receive messages, it will perform some local computation, and it will send messages to all of its neighbors in the communication network. And this basically defines the behavior of a node in round T, in a particular round. So when you try to simulate L congest rounds in MPC, you just need to collect a ball of radius L around the vertex that you want to simulate. And this ball will have size at most delta to the L, and you can collect it in O of L MPC rounds by just collecting it one hop at a time. And of course, this is assuming that this delta to the L size ball fits in the memory of a single machine. But you can actually do a lot better by this graph doubling technique. So let's assume inductively that we have a ball of radius I around this orange neighbor, and it has these blue nodes in its I hop ball. And also we kind of computed I radius balls around all of these vertices in parallel. So if we gather all of these I radius balls at the machine, gathering the ball for the orange vertex, we can just get the ball of radius 2i around the orange vertex. So we get a delta to the L size ball of radius L in log L MPC rounds, assuming everything fits into memory. Right? And the main idea in this paper, the main ingredient that we use is we use sampling information through the algorithm to somehow reduce the size of this ball. So basically, let's say we have some information from the algorithm that tells us that these two vertices, the gray vertices, do not speak in the next I rounds. Then we can just not gather the balls around these two vertices and still get a 2i radius ball, which is much smaller, and still be able to simulate L-hop congest algorithm around the orange vertex. So we have a much smaller ball of radius L that is collected in log L MPC rounds. And because this ball is much smaller, we can make L larger to kind of simulate more congest rounds in congest rounds much faster. So this leads us to this sample and gather simulation theorems, where we observe that many congest algorithms involve rounds where only a sampled set of nodes is active. And if we can estimate these sampling probabilities quickly, we can use them to subsample a ball of radius L so that it fits into memory. This allows us to get simulation theorems where we simulate an R round congest algorithm in R over square root log n base alpha MPC rounds. And here this alpha controls the sampling probability. I won't be able to give intuition as to what alpha is beyond this sentence for this short talk, but you can look at the long version or the paper as well for more intuition as to how alpha actually controls the sampling probability. So what happens is that we get these we have these R congest rounds we want to simulate. We take chunks of size L, which is square root log n base alpha, and we use our simulation theorems to simulate these L rounds in roughly log n MPC rounds using the graph doubling and sampling techniques I described earlier. And so this allows us to go from R congest rounds to R over square root log n base alpha MPC rounds. So our simulation theorems are in fact inspired by a previous work due to Benezad et al. This appeared in PodC 2019. There they show a simulation theorem that runs an R round congest algorithm in roughly R over log n base delta rounds. So notice that if you simulate a log n base delta hop delta rounds of the congest model, let's say you simulate epsilon log n beta, then a ball of radius L will have size n to the epsilon, because it's n raised to it'll be delta raised to epsilon log n base delta. But these simulation theorems are very weak. In particular, when delta is roughly linear, this doesn't give any speed up. But if even in this setting, if the algorithm allows us to sample a small set of, then our simulations give a much better speed up. So why would we even want to consider simulation theorems? These simulation theorems allow us to connect complexities from classic models like PRAM or congest to the newer models MPC. And it also makes it easier to port existing algorithms and also to design new algorithms, because at least for me, designing algorithms in the congest model is a lot easier than thinking about a newer model with different communication patterns. So let me end with a few open problems that are left from our work. So the main open question is, can we get a polylog n round beta ruling set algorithm for some constant beta? This was the question that initially motivated our research, and we quickly realized that this is not really possible from the current techniques that we have. And the current techniques only allow us to get a log delta raised to some constant time for beta ruling sets. And this open problem is, can we get deterministic versions of our sample and gather theorems? In our simulation theorems, we actually use random coins to do the sampling process. So we actually randomly sample a set of active nodes for the L rounds that we want to simulate, and we gather the balls. Maybe we can somehow get a deterministic procedure to do this for certain cases. More concretely, can we get a little O log n round MIS algorithm in the low memory MPC model? And finally, can we show more general versions of our theorems, simulation theorems, in the linear memory MPC model? This graph doubling technique has been a lot more successful in the linear memory MPC model, giving us log n algorithms for MIS and approximate vertex cover and matchings and so on. And with that, I'll thank you, and I'll have any questions that you might answer. Any questions.
It was a long talk, but it was a long talk of the long version of the talk. So, okay, so now we have a couple of minutes for questions. Anybody has a question? Let's see. No, there is no question in chat. So let's unmute ourselves and thank all the speakers of the session and for such a wonderful session. And yeah, so thanks to all of you, and see you later. You can also go to Gather and have some discussion. So I think there will be a business meeting around 7 o'clock, and there will be invited talk at 8:30. So bye-bye to all of you. See you. Bye.